Okay. So now we'll sort of continue with the um, ROC portion of this, where we have, it's recorded. I think it's recorded at least, yeah. So we're now focused on sort of a specific practical example for self-driving cars. And so this is where you want to be able to find the road in the image. And so we have sort of this color image that we're looking at, and we can see as people quite easily that the road's there. We have very little information in sort of the quantitative sense to go by. I mean, we could say that roads are supposed to be kind of gray or black, but as you see, this part of the road is really well illuminated, this part is not. We don't know anything about the illumination, we can't really control that, and so it's really not easy to say this is the definitive threshold that we should always use. We need to come up with sort of more, a better way for doing that. We can't use the sort of model approach, we need to use the sort of machine learning based approach. And so the first step for this is to come up with the ground truth. And so this is the painful reality of coming up with such sort of data, is that you need to then manually or have someone label or get from another source of information this segmented image where you can say that this is the road and this is background. And so that matches up quite well with the data that we have here. And someone manually drew this out so that you have that as sort of a comparison. Unfortunately, there's not really a better way to do that. Otherwise, you have to manually count pixels every time, or, I mean, you can't come up with a quantitative metric unless you've done this. And so now what we can do is we can try sort of a simple segmentation where we say, okay, anything below this certain value is road, and everything else is background. And we see that this does a pretty terrible job of identifying the images. And so we have the sort of road and background, and then we have the different categories of false negative, false positive, true negative, and true positive. We can then start to change this cutoff criteria that we have, and we sort of see how the pixel count changes. And so now that we're dealing with a whole image, this is much larger, and so these scales change a lot. And then we have sort of this precision recall curve, and unfortunately we're much further away from this perfect point than we'd like to be. So the curve we had before was something like this, and now we have a curve that looks more like that. And so that's unfortunately the reality with a lot of these situations, is that a very simple approach, like just taking a threshold, is very, very far away from what you ultimately need to bring in order to get a good result. We can then sort of plot the curve in the other direction where we see this random guessing line, and we see that for very low threshold values, we're actually worse than random guessing, which sort of makes sense, that if you sort of have a very low cutoff, then you're going to have lots and lots of things that are not road being identified as roads, and lots of things that are road that are not being identified that way. And so this is sort of the reality, and is, if you're above this curve, that's good, but if you're below this curve, then you're actually not creating any new information with your algorithm. You'd be better off not using the image at all. Of course, if you're really below the curve, and so if you have a curve that looks like this, that's not necessarily a bad thing. I mean, that means that you're quite close. You just sort of need to flip the sign. And so you need to change that your threshold, instead of being lower than, needs to be greater than, or your criteria need to be shifted so that you get that in sort of the right corner. But having a really bad curve is also useful. It's only a problem when you're close to this, because if you're close to random guessing, there's nothing you can do to get away from that. Or you need to sort of radically change what you're doing to get away from that. So one of the other things we can do is sort of bring other pieces of information into this image. And so this is where we can say the road is in the bottom right corner, or in sort of the bottom and the right part of the image. And we can say that sort of let's blur out the features a little bit. So this is just a small blur, but we could do a much larger blur. And so sometimes we use this blurring to get rid of noise, but it can also be helpful for sort of getting rid of small features that we don't want us to be distracting. So for example, with this road, there's these stripes in the middle, and we want to minimize these stripes as much as possible because they make it more difficult for us to see the road. And so blurring this and trying to make this as flat as possible, while not typically the task in image analysis, in this case can actually improve what we're trying to do. And so that we then see these curves that we have at the end, where we have sort of this precision recall, and we can kind of progressively get better and better using these different approaches. And so especially compared to sort of the standard approach, using this region instead of it made a huge difference. And so it brought us much, much closer to sort of this final segmentation. And this blue curve is wrong, but I'll fix that later. I think it wasn't updated correctly. But yeah, so the blue curve should then even be higher than this because that blurs out a lot of the small features that we have. And so when we look at that metric we mentioned before, the area under the curve, this area, of course this curve extends out to there, down this way. And so we can see that the area under this curve is double or more of that of the original curve, probably 4 times higher. And so that this is clearly a much better approach for segmenting the image than we had before. This is not an entirely invented problem. This was a problem that we actually had. The problem was more to find crosswalks. And so what we did there and so that was one image, and I think we have another one there somewhere as well. That's not the good one. So where you're trying to find crosswalks in sort of these images, and it's important to be able to identify things that are crosswalks correctly and things that are not crosswalks correctly as well. And so here, even though there's a shadow of a tree, you need to have that sort of eliminated from your image. And so that's where these sort of problems come from. But of course, to do this is much more complicated than a simple threshold. So this involved a number of different filters, transforming the color space so that you were focusing on the colors that were of interest, and you could sort of take out illumination as a factor, and looking at shape. And so when you're looking at crosswalks, you know that these are supposed to be stripes. And so you can sort of enhance the line-like features and group them together in order to find them. And so, for really solving this problem, you need to bring in another more complicated approaches, but the way you assess your solution is ultimately the same. You come up with this sort of curve, and you try to constantly improve this curve or improve this curve in the regions where it's important for you. Cool. So now, that sort of finishes the machine learning part. Are there any questions on that in particular? Okay, so now we can move on to kind of other image types. And so this is what we mentioned a little bit before with the thresholding, is that a lot of the image data that we get has multiple channels or has multiple pieces of information inside of it. And so here's sort of an example where we have kind of a 4 or 5 dimensional data set, where each point, rather than being just a pixel, has a shape assigned with it, an orientation, and an intensity. And so we have a lot more information to look at. And sort of, instead of just having one histogram that we're analyzing, we have now 4 different histograms to analyze. And so we can look at sort of the connections between them by making sort of one of these cross plots where you see what's the relationship between A and B and theta and the color that it has. And that helps you see, okay, these ones are fairly well correlated, A and B. And so it doesn't make sense to look at them independently because they're not really providing you new information. And when you see things like this, then you see that they're completely uncorrelated and that these might be useful sort of independent components to look at. What we move on to after that is sort of the segmentation of multiple phases. And so what we do, particularly in X-ray imaging, a lot of is that you'll have a sample measured that has a number of different phases inside of it. And so in this case, we're looking at a shale sample. And so there are there's clay, rock, and air inside of the sample. And so we have, if you look at the image, your eyes, again, see very quickly that, this is white, so this is very dense. This is sort of a gray material, and this is sort of a darker material. And so what that means is that that's probably air. These bright spots are probably rock or dense materials, and this is then the clay, the sort of gray medium that everything is inside. And so your eyes can separate that very easily, but for a computer it's much more difficult. We would ideally come up with 3 values based on sort of a model that we know this is how much this dense material or this rock absorbs. We know how much clay absorbs, and we know how much air absorbs. The problem is that we have sort of a noisy image, a noisy detector in constant illumination. And when we look at our histogram, if we wanted to see 3 phases, we want to have 2 distinct peaks, or 2 distinct peaks that we can, or 3 distinct peaks that we can separate, so that we have the points where we threshold, where we say this is the cutoff between air and clay, this is the cutoff between clay and dense materials. And so here we see that there's 1 peak very clearly, but then it sort of fades off. And so to try to divide that evenly into 3 different regions is going to be difficult, and we're going to have problems trying to do that. We also have the problems that with clay in this image, the clay doesn't really have a constant absorption. It sort of shifts based on how densely packed it is. And the exact mineral composition we don't know, or the chemical composition we don't know. And so it's hard to define a single value that would encompass clay well into this image. And so what we can do is we can sort of arbitrarily assign okay, this is void or air, where it's between 0 and 0.2. This is clay, where it's between 0.2 and 0.5. And this is rock, where it's basically anything above 0.5. And so we end up with these different phases in our image, and it's sort of divided like this, so that you have the different divisions there. That shouldn't be green, but anyways. One of the things that we see quickly with this is that we have clay there. We have rock here. So void is the least absorbing, clay is the middle, and rock is the most. And so it sorts them alphabetically, but that isn't, of course, matched up with our absorption value-based description. But what we see with this is that we have sort of rock areas, and outside the rock areas is sort of, or between rock and void is clay. And we have the problem that if you have pixels that are right next to each other, that have, one of them has a very high absorption level and one of them has a very low absorption level, that you end up with sort of the average between them. And that if you're trying to divide it into 3 phases, that you find things in this middle phase in places where it doesn't necessarily belong, because you have these 3 different phases that you're looking at. And so basically, if you have a pixel that's half rock, half void, that will be classified as clay, when in fact it doesn't belong to either of these groups. And so I don't think I have the sample here, one of the interesting examples we had for that was where you would have, where it looked like from the imaging data when you did this simple segmentation, like all of the sort of rock samples were coated in clay. But that wasn't the case at all. When you sort of examined the sample closely and took it apart, it was just that when it's surrounded by void, as it transitions from rock to void, it goes through this intermediate absorption value, and because you have a discrete image and a very simple classifier, you identify that as clay. And so all of these really thin layers of clay around the sample were entirely imaginary. And this is a fairly significant problem with data sets like this, and this is only with 3 different phases. When you try to extract 4, 5, or 6 different phases, this can be then very, very problematic because you don't simply have the overlap between 2. You have the overlap between 3 or more different things that it could possibly be. And if your features of interest are small, this can be a huge challenge to try to do something meaningful with the data. So now to move on to kind of sort of implementation. And so implementing these sort of analyses are quite easy because it's a function basically that you apply in your image, so a unary operation where you have your image come in and you apply it and you get the output. And so in mathematical terms, this is usually called a map. And it's very easy to apply sort of in parallel because you don't need any other information. You can look at each pixel completely separately from all the pixels around it. And so that's one of the things that makes this very easy to do, particularly at a large scale, because you don't need any other information. You just need the information from the pixel that you have. Filters, like what we covered before, are much more difficult because it's more challenging to separate it into separate pieces. And so with filters, you then have to look at not just a single pixel, but the neighbors around it. And so when you have to include the neighbors in this analysis, it becomes much more challenging of how you divide your image and how you can handle that well or efficiently. And so we have sort of examples of what the code to do sort of a threshold looks like in a number of different languages, in case you're interested. And then, yeah, so sort of the pitfalls that we have with segmentation are sort of, this partial volume effect, which I sort of mentioned before. And this is really where you use pixels or voxels to look at your image. And these are a poor representation of reality. And so if you're looking at a sphere or a circle, there's no way that you can describe a circle using square pixels. It's simply not possible. So some of your pixels are going to be partially filled with material, partially empty, or partially filled with two different materials. And so this is generally called the partial volume effect, and it makes it very difficult to do segmentation reliably because you're trying to describe a shape with something that it doesn't have anything to do with. Of course, if all of your features are perfect squares and they're aligned with your imaging plane, then you can describe it well with voxels. But as soon as you have real features or unsmooth surfaces or spheres and things, it becomes very challenging. So what you see is that for small objects in particular, this is a much larger problem than for larger objects. And so if you have a huge object, the fact that you're making it up with tiny little squares doesn't make that much of a difference. But when you have a very small object, it can make a huge difference. And so this will be particularly important in the future lectures where we talk about what sort of shape analysis and other approaches we use. Because if you're trying to compare the shape of this with the shape of that, you'll get very different results because this shape is being poorly approximated by these pixels, and this shape can be well approximated by it. And so here you can see sort of the distribution you have as you sort of increase the radius. And so if you have a small radius here of 2, then you just have values that are 0 and 1. And as you increase it, you get sort of a much larger spread. And so we see here that the mean intensity of the image is 0.3, and that mean goes up and the standard deviation goes up as this circle gets larger in shape. So now one of the other tools that we'll briefly mention, you can then look at sort of the rest of the slides on your own, and we'll start the next lecture with this material as well, is this idea of morphology. And so has anyone heard of morphology before? So erosion and dilation and those sort of approaches? Okay, so we'll cover that. And so morphology is sort of when we have this original image that we've segmented, and we now want to improve our segmentation. And so it's often quite messy because all of these things don't fit perfectly well together. And so morphology is once you've segmented it, how you can improve that segmentation, how you can take these binary pixels that you have and make them represent what you want them to represent better. And sort of where this can be kind of confusing, or where we've seen a lot of students struggle with this, is the fact that you have this problem of you can do the same things with morphology that you can do with image enhancement and filtering. And so they have the same goal, but they come in at different points in the process. And so understanding exactly what makes this unique or how it's different is sort of the important part for this part of the lecture. And so basically what we have is that we have this collection of pixels that we've come out, and ideally before we do the threshold, we've done as much image enhancement as we possibly can. And so we've already tried to get rid of the noise and tried to do filtering and smoothing as much as we could. And then we get our threshold image out. And we use morphology because that still doesn't match perfectly what we want to have. And this basically is a slightly stronger approach than just filtering because it's more aggressive in how it handles the image. And so it sort of is an all or none kind of approach, which allows it to change your image more quickly, and it only looks at sort of binary values, so 1 or 0. And so we have this idea of sort of a neighborhood, which is something we mentioned briefly in this image enhancement lecture. And this neighborhood is really the pixels which are around the current pixel that you're looking at. And so you can have a large neighborhood, and that performs operations over larger volumes. And that's computationally very intensive. And it can smooth out features that are of interest to us. A smaller neighborhood looks at smaller volumes, but it struggles with large noise or to fill large holes in your image. And so neighborhood is really important for a lot of the other things we'll discuss in the future. And for morphology, it's critical. For filtering, of course, it's also important. Component labeling, distance map, and image correlation tracking methods all use this idea of neighborhood. So kind of being comfortable with that and knowing what it means to have different neighborhoods or what the different options for neighborhoods are is very important. So in 2D, this is fairly well defined. So you have your current pixel of interest here, this blue, and you have a sort of 2 different types of neighbors that you can define. The first type is really the 4 adjacent, which are the directly above, directly below, right and left. And the next one are the 8 adjacent. And so those are the ones where you look at the diagonal. So the other way you can describe it is the 4 adjacent are the ones that share an edge with this pixel, and the 8 ones are the ones that share only a vertex. We can also define them in sort of a distance term, where you have the ones that are exactly 1 unit away from the centers of this pixel to the center of this pixel are the 4 adjacent, and the ones that are square root of 2 away are the 8 adjacent. You can then do all of this in 3D or ND as well, where you can say instead of 4 adjacent and 8 adjacent, you have 6 adjacent, 18 adjacent, and 26 adjacent. And so you have your pixel of interest in this middle, this 13, and the ones that share a face, which is shown as a red line in that image, are the 6 adjacent. So those are the ones directly above, directly below, directly to the right, directly to the left. So they're really sharing a face with this. The ones that share an edge, which are shown as sort of the yellow lines, are the 18 adjacent. And so that's the ones that are also here and here, but they're not sharing a face. And then the ones that are sharing a vertex, which are these purple dots, are the 26 adjacent. So you sort of move up. You could, again, use a distance metric to define it, where the ones that are 1 unit away are defined as the 6, root 2 units away are the 18, and root 3 units away are the 26. And so, of course, in 4D, this becomes more complicated, but it's not as common in visual problems to have 4D. Usually you have 3D, and then you have sort of different depths, or you have different time steps or something. Is this sort of clear to everyone what this definition means? And that when this definition is particularly important, or it's important to sort of consider, is when you think about your system that you're trying to understand. And so if you're looking at sort of a diffusion process, for example, then the ones that share faces or that share edges in 2D are the ones you're going to be most interested in, because something can't flow through a vertex or through an edge in 3D. In order for something to flow, you need to have an area. And so when you're trying to decide, are these pixels in the same neighborhood, then you want to have something that's defined where the neighborhood has that shared face, because that means you can have a flow going across it. And if it only has a shared vertex, then there's actually no material that can go through there. But if you're looking at sort of structural support, then maybe the edges can be important because you could have weight being born on one of these edges, and that would not work probably on a vertex, but it would work better on a face. And so it sort of depends on what sort of analysis you're trying to perform, or what scale you're looking at. And so if you're looking at diffusion of large objects, of course the face is important, but if you're looking, is it possible for a virus to spread through this part of the cell and the virus is 1,000 times smaller, then the vertex being shared would be important for you. So when we take these erosion and dilation operators, which are really the basis for what we have with this morphology, the erosion is really peeling a layer off of the surface. And so if any of the voxels in the neighborhood are 0 or turned off, then the voxel itself will be turned off. Dilation is then the opposite of this. And so this is really adding a layer onto your component, which basically says if any of the neighbors of this voxel are on, this will be turned on as well. And so, for whatever reason, that slide. So these slides are the same as last year. And so if you go to if there's something that doesn't work, you can go to last year's slides and look at it. So what we have is we have this image that we had before. So this cross where we tried to threshold it, and there's sort of lots of holes in the structure. And so what we can use with these erosion and dilation operators for is to try to fix that. And so if we take this image and we perform a dilation, it turns all of the pixels in the image on, or adds all of the pixels to the structure, where one of their neighbors is part of the structure. So we go from having this pink image to having this sort of blue image where that's much better filled in. And so if you were trying to do character recognition on this cross, it would be much easier with this image than it would be with that one, because it then it's filled in properly and everything's connected together, and it would be much easier for a system to try to understand that. Similarly with erosion, if we sort of have a threshold in this case that's probably too high, you can then perform erosion to get rid of all of this outer layer of pixels so that you don't have all of sort of this noisy background anymore. So all of these single pixels by themselves are deleted because they have one neighbor which is off. The problem we have, or can anyone see what the problems might be with using analysis techniques like this? Yeah.
You can't reconstruct the volume anymore because you don't know if you added something at the edges or you put something out of it.
Yeah. So that's exactly the problem. So when you do something like this, you change the volume. And so if you're trying to do further analysis on your image and you perform one dilation, then the volume, I mean, of course, you can't say exactly what the volume of this would have been, but if you look at the area of this, you can sort of imagine that the cross was supposed to look something like that, and that these holes in the middle were simply missing. And now, once you've done the dilation, you have this whole extra layer on top. And so you're not really able to say that that was the area of this cross, because you've made it bigger. Yeah?
Imagine for both of these algorithms, you can choose what type of edges you want to find as edges. So you could say do dilation considering only the surface-to-surface or edge neighbors, or considering only the vertices.
Yeah, you can, but you're
That's
still
where the neighborhood types come into play.
right. But you still, with the dilation, you're always making
Right.
more. And so if you're trying to assess what area you have, your area is not going to work. And so with erosion, you then have the same problem. That this was, you wanted to get rid of these pixels here, but you got rid of all of these pixels here as well. And so if you're trying to say what the area of this is, it's then smaller than it should be. So that's where we have these sort of more complicated operations that come in, called opening and closing. And so opening is sort of the idea that you open up your image, so you disconnect things, and you get rid of small objects. And so this is an erosion followed by a dilation. And so it peels a layer off and then adds a layer on. And so very small objects are deleted, but the normal objects, or sort of the core objects, are kept. And so, the standard way of looking at this is sort of a cube. If you apply this operation to a cube, the volume at the end is the same as the volume at the beginning. And so you don't change that volume at all. Closing is then sort of the opposite of this opening. And this is a dilation followed by an erosion. And so sort of the easy ways to remember that is sort of the opening is you're opening up your image, you're sort of pulling things apart. And the closing, you're sort of connecting things together. And so this adds a layer and then peels a layer off. And so objects that are almost touching, or that sort of have a few holes in them, will have these holes filled in. And then the image is sort of closed and connected. And a cube, again, when you provide a closing, will have the same volume before and afterwards. So we can see that for the two images we have here, with the opening, we get rid of all these stray pixels along the side, but we keep this core cross well, and so the area of our cross is very well preserved. And with the closing, where we have sort of this holy cross, we then fill in the gaps well. So there's still this sort of problem with the surface that we don't count all of those, and maybe they should be counted, but it's ultimately kind of a judgment call. And what we see is that these operations keep us much closer to the original image we wanted to have than just the erosion or the dilation on their own. They're not perfect, but they help us stay there. Boom. And so this is where morphological tools can kind of get applied. We have here an image of a bone slice. And so this comes from a slice of sort of cortical bone out of a hip, where you want to find out where the bone is. And so if you want to say, this is a cell, so you have sort of in this two phases that you've easily identified, this is bone and this is air. But this is air outside and this is air inside. And so how can you classify them into different areas? And how do you know that this is inside the bone and this is not? And how do you define these sort of inlets as being inside the bone or not? And so this is where we can use these tools to try to fill in the holes that we have in our image. And so we can also perform these steps that we've talked about before iteratively, so that they can fill up larger than just one voxel or two voxel holes. So you can either use a larger neighborhood, or you can apply the same operation over and over again. So what we see with this image is if we perform a 3x3 closing, this is the image before, and the image afterwards has then these holes filled in. So you have sort of the smaller holes are now blue, and so they're filled in. You can then perform a 7x7, and then some of the larger holes are filled in, but some of the features here are connected. And so this is then counted, this area here, as being inside the bone, even though it technically is probably outside of it. You can then do a really extreme operation of like 45x45 closing, and then you've closed all of the holes that you have inside your bone, but you now have this whole region here, which is being considered part of the bone, even though it's clear from our eyes that that's outside of it. And this is because you have these artifacts of using such large blocks and sort of non-perfectly cubical shapes, that these shapes start to get approximated by cubes when you perform such large operations on them. We can then see that the volume fraction that we have is sort of constantly increasing as we increase the closing size. And so using a larger closing size at some point shouldn't increase your volume fraction anymore, but it does because it's not a very good match for the shapes that we're looking at. And so this is where you sort of need to make a judgment call of how many of these features do you want to include, or is this the right tool for sort of closing your image and filling in your holes? Boom. You can also use sort of different kernels. And so we defined the neighborhoods before. Another way to call them is sort of kernels. And so you can have sort of circular shape, or you can have the full, which is sort of what we define as the 26 neighbors or the 8 neighbors, where you have sort of the edges as well. You can also have a circular shape where you sort of only include the ones, you don't include the ones at the edges. You can have a horizontal line where you just include the ones that are sort of in a horizontal line, or the vertical line where you just include the ones that are in the same vertical line, or a diamond shaped where you just include the one sort of directly above and directly below, but scaled up to the dimensions that we have here. And so that we can see this volume fraction is very largely dependent on what shape of a kernel we use. And so with many of the kernels, this sort of increases without end, but if we use sort of a vertical line, at some point it sort of saturates and stops growing as much. And so for maybe filling in the holes, using this vertical line is a better approach because it doesn't sort of grow endlessly. You also have sort of other techniques like convex hole or flood filling, which can solve this problem as well and bring in other sorts of issues. Boom. This will be part of the exercises, I think. But we have some fossil data measured at a synchrotron where you can actually go through it and try to figure out what features they looked at, if you're interested in, and try to segment them out yourself using some of the 3D viewers. But that's not the primary focus. So, are there any questions over that stuff? Okay.